Hey everyone, I'm Dan Fullerton, and welcome back. Today I want to talk about Faraday's law and Lenz's law as we continue our study of electromagnetic induction. Our objectives include recognizing situations in which changing flux through a loop will cause an induced EMF or current in the loop, calculating the magnitude and direction of the induced electromotive force, EMF, and current in a loop of wire or a conducting bar when the magnitude of a related quantity, such as the magnetic field or area of the loop, is specified as a nonlinear function of time. And finally, analyze the forces that act on induced currents to determine the mechanical consequences of those forces. So let's start by talking about Faraday's law. The induced electromotive force, EMF, or induced potential difference, if you prefer, induced voltage, due to a changing magnetic field, is equal in magnitude to the rate of change of the magnetic flux through a surface bounded by the circuit. And the direction of that induced current is given by Lenz's law. So, in mathematical terms, the induced EMF is equal to the opposite of the change in the magnetic flux as a function of time, which is equal to the opposite of the rate of change with respect to time of the integral of B dot dA over an open surface, which is equal to the integral over the closed loop of the electric field dotted with dl, where the closed loop bounds this open surface. Taking a look here, we have a magnetic field coming through a loop of wire down here. This would be our magnetic field. This would be our closed loop or our open surface. So really what Faraday's law is telling us is it's telling us how to find the induced potential difference or the induced current due to a changing magnetic flux. Now, these negative signs here, those negative signs are really Lenz's law, which tells you the direction of the induced current, induced potential difference, or magnetic field. And we'll talk about that separately. So if the negative signs worry you, that's just another way of writing Lenz's law, and we'll clear that up here in a minute or two. So Lenz's law says that the current induced by a changing magnetic flux creates a magnetic field opposing the change in flux. This is how we get the direction of that induced current. For example, here we have a bar magnet being pushed into a loop of wire. As it's pushed into that loop of wire, we're going to have more flux pointing in this direction going through the loop. The induced current wants to oppose that. So if I draw that in the opposite direction, the induced current wants to create a magnetic field, magnetic flux, opposing that change, so upwards. And if I follow the right-hand rule and point my thumb upward in that direction, I'm going to see that I'm going to get a counterclockwise current there, which is why you see that the current flow is shown as going counterclockwise in that loop. To put it another way, or to look at a similar situation, let's redraw our magnets. There's north. There's our south pole. And we'll draw our magnetic field lines the same way again. There we go. And our loop of wire. Something like that. But now we have our magnet being pulled up, away from that loop. So as it's being pulled up, the flux through this surface is decreasing, which means the induced current wants to counteract that change. It wants to go back in the same direction. So now by the right-hand rule, I point the thumb of my right hand in the down direction and wrap my right-hand fingers around it. And what I see then is that I'm going to have a current flow in that direction, clockwise now. So, ways to use the Lenz's law to tell you the direction of the induced current. Now, another example here. If we have the magnetic field going through this loop of wire, if B is increasing, then we're going to get an induced magnetic field that wants to go in the opposite direction, or that direction. Right-hand rule, as I take a look at that, point the thumb of my right hand into the plane of the page or the plane of the screen. The fingers of my right hand wrap around it in a clockwise direction. If instead this was decreasing instead of increasing, as that field is decreasing out of the plane of the page, The induced current wants to keep it the way it was, so it's going to add to the magnetic field coming out of the page, so you would get a counterclockwise current. Lenz's law takes a little bit of practice, but once you have it down, you'll be all set. Once you have it, it's pretty easy to use. Now, at this point, we've covered Maxwell's equations. First of all, Gauss's law. The integral over the closed surface of E dot dA was the enclosed charge divided by epsilon 0. Or for magnetism, the integral of the closed surface of B dot dA equals 0. And that only worked because there were no magnetic monopoles. We've also now talked about Faraday's law that says that the integral over the closed loop of E dot dl, which is the induced potential difference, or the electromotive force, is equal to the opposite of the derivative with respect to time of the integral over the open surface of B dot dA, where this open surface is defined by this closed loop. Now, a key point here, we've talked about Kirchhoff's voltage law when we were doing our circuit analysis. Kirchhoff's voltage law is a special case of Faraday's law when the magnetic flux is constant. If you have a changing magnetic flux, we can no longer use Kirchhoff's voltage law. We'll have to use Faraday's law to sum up potential drops around a closed loop. So Kirchhoff's voltage law only works when you have situations of constant magnetic flux. If it's changing, we have to go back to Faraday's law here. And finally, Ampere's law. The integral over the closed loop of B dot dl is equal to mu naught times the current that penetrates that closed loop. And there's a little bit more here, which is why I put the asterisk. We're going to have to add just a little bit to that to close off Maxwell's equations, but we'll get to that in a later presentation. All right, let's take a look at a couple samples. A magnetic field of strength B as a function of time is given by 3t squared minus 2t plus 1 is directed out of the plane of a circular loop of wire as shown. There's a lamp somewhere in the loop, but it's not shown. Find the generated EMF as a function of time. Well, to start there, the induced EMF is equal to the opposite of the rate of change of the flux with respect to time, which is the opposite of the derivative of the integral over the open surface of B dot dA, which in this case is just going to be minus d over dt, and B is constant in this case, and the integral over the open surface of the area is just going to be that area, so BA, which implies then that the induced EMF is equal to minus, well, the derivative of a constant, that area, is just going to be that constant. Minus A comes out of the derivative sign, and that's the derivative of the magnetic field with respect to time. So that's minus A times the derivative with respect to time of, well, our magnetic field function is 3t squared minus 2t plus 1. Which will then be electromotive force is equal to, well, we'll have minus, our area is just going to be pi times r squared, area of a circle, times the derivative of 3t squared minus 2t plus 1 with respect to t, which is going to be 6t minus 2. So there's our induced EMF. E equals minus pi r squared times the quantity 6t minus 2. Let's take that a little bit further now. Determine the current through the 100 ohm lamp as a function of time. Well, current is just potential difference divided by resistance. So that's just going to be minus pi times r squared times our quantity 6t minus 2, all divided by our resistance, 100 ohms. All right, and let's take a look. One more piece to this question here. What is the direction of the current through the loop at time t equals 5 seconds? Well, to do this, let's recall that the derivative of the magnetic field with respect to time was 6t minus 2. So if I want to evaluate that to see what the rate of change of the magnetic field was at t equals 5 seconds, the derivative of b with respect to t evaluated at t equals 5 seconds is just going to be 6 times 5 seconds minus 2, or 30 minus 2, 28. Well, 28, that's a positive number. That means it's increasing as the magnetic field comes out of the plane of the page. Well, if that's increasing, then the magnetic flux, the induced current, is going to create a magnetic flux that opposes that change, or would be decreasing. Point in your right hand into the plane of the page, opposite the direction you already have the magnetic field, and wrap your right hand fingers around it, and you'll find that you would get a clockwise induced current due to Lenz's law. So our answer there would be clockwise. Okay, let's take a look at one more example here. Consider a circuit in which a current carrying rod on rails is moved to the left with constant velocity v. If the circuit is perpendicular to a constant magnetic field, determine the induced EMF in the circuit. Well, we'll start again by realizing the induced EMF is equal to minus the time rate of change of the magnetic flux, which is the opposite of the time derivative of the integral over the open surface of B dot dA by Faraday's law. Well, that's going to be, well, B is a constant in this case, so that will end up being minus B, and the integral over the open surface of dA is just going to be that area, and the time rate of change of that area, well, L isn't changing, but we have V changing, which is dx dt. So that's going to be minus L dx dt. But we know that V equals dx dt. So I could write this then as the induced EMF equals minus B L times the velocity, V. And you might have learned that equation previously in an algebra-based physics course. The induced EMF due to a rod moving to the left here in a constant magnetic field through that area of that rectangular loop. All right, hopefully that gets you a nice start with Faraday's law and Lenz's law. If you need more help or more information, check out aplusphysics.com. Thanks everyone, and make it a great day.